Okay, I'll just put the characterization sequence in perspective in about, I'll cut short by 5-10 minutes if possible so that I make up for the time lost. Okay, I'll just go through the surface, this thing. So, physicist Pauli just made this statement. God makes solids, but surfaces are the work of devil. Okay, the whole thing, okay, it's so crucial. Surface is the one which damages. Where material degrades, fails, everything that happens which you don't want to happen to the surface is mostly from the surface. At the same time, many things also happen, okay, like catalysis happens in the positive form, but whatever it is, if you have to understand, that is where it is. Okay, it's a very complex phenomena. Okay, and surface sensitivity, cleanliness is extreme importance in this analysis. And what is the surface? When the surface, whatever liquid or gaseous phase and the solid phase, okay, what differentiate is the surface, and the surface is never having the bulk structure. It's having a very different structure. Whatever is your material, you think that so-and-so is your material, but it is not that. It is something different, what is existing. So the whole surface characteristics is very, very different. It behaves differently, its structure is different, its many things are different. The whole of its electronic structure is relaxed, it just behaves differently. You need to understand. Okay, that is where many properties, okay, surface properties are of great importance, are all related to surface. Just if you take one particular surface context, a coating, but a metallurgical coating. Okay, you have the coating, you have the substrate, you have the interface layer. So many things of importance are there to be understood. You have a coating, but how many things you have to control, understand, and design properly to have a good coating, these are all listed. So many listed. So that is where the relevance of surface comes. Now, we define surfaces in various forms. Okay, when we say surface, in different application for a different individual or different scenarios, it is having a different sense like. Okay, surfaces can be as thick as or even larger than a few micron meters, 10 or 20 or 50 micron meter. That is one category of surface, and surface can be angstroms level. In catalysis and all, the topmost monolayer or a fraction of a monolayer is what is going to really affect the whole this thing. So it just has various definitions, and at each one of these regimes, various phenomena, materials phenomena are all there. So the application is really vast, really vast. And now the whole general process of characterization, if you take, what you are just looking at is you are having this physical phenomena, various physical phenomena. One is the absorption, inelastic scattering, diffraction. These are all the material interaction possibilities which you are going to exploit to obtain information about your material. Okay, you have your incident radiation put on to that, and then you have this thing. Your data comes in these various forms. Okay, you are interested in this. Okay, and these are the effects that will be there leading to that data what you are obtaining. Okay, there are various techniques, analysis techniques. You may be interested in structural information. You may be interested in chemical information. This list is not very complete, but it is suggestive. The variety of techniques available, as you go from here to here, it is having better resolution, better capability of giving you information at a lot more localized level. So if you take imaging, in structural information, you will have crystal structure imaging information, and also materials microstructural information. You begin with the optical microscopy, okay, and it has a limited resolution. It has a limited resolution of about, the best is 200 nanometer. That is where you begin. Then this can give better, this can give better, and these are the ones which can give you atomic scale information. Latest in this is your AC temp, okay, aberration corrected temp, which will give you a fraction of a angstroms is possible. Okay, and we have just been able to go to that sort of a level. Again, when we look at the composition, okay, chemical information, these are TDS is there, these are technique. When you talk about surface, this is near surface, this is a molecular level, this is the actual surface information. So you have a XPS, and this is a scanning OJ microscopy. This is your secondary ion mass spectroscopy. Okay, this is your scanning tunneling microscopy. Okay, as you go from here to here, this is almost like a very vast, large number of large area analysis. Okay, but a surface analysis. But here you go almost to atomic scale information line. Okay, now the whole surface analysis technique, if you take, again, you just can list out certain major ones have been listed out. The particle what you are going to send to probe the material is listed out here. Okay, and the process what is happening. The particle what you are going to measure, the signal which is coming out is listed out here. This is the process what happens. Okay, in OJ, you are sending an electron. What is output is an electron. This is your material, and you can handle, okay, except hydrogen and helium, all other elements here. This shows the monolayer sensitivity, okay, of the technique, and the depth probing. Okay, this is 20. You just compare this with the XPS. It's a little better than XPS, and it can also do your analysis from lithium to uranium, both of them. And these are the technique. Just these two, I'll just give the possibilities and analysis a little bit, and just come towards this and then hand it over to our expert to carry forward from there to talk about XPS and AES. Okay, and if you see the monolayer sensitivities for these techniques, it's a fraction of a layer for these techniques. That is they are extremely surface sensitive, they are surface characterization techniques. As against that, okay, these techniques are just more of a bulk analysis. Okay, bulk analysis. When you take XCM, there are various possibilities. And now our facility is giving you all these accessories. Okay, the SCM capability what we have, okay, you name it, it is there. Much more it is there. Some hot stage, tensile testing, many possibilities are there. That is how our lab is really very well equipped. The whole basis of this analysis, the resolution depends on interaction volume. Depending on the interaction volume, you have different modes of operating a SCM, and it has a different lateral resolution, different depth resolution. Why I am including this also a little bit as a preliminary part to just bring the whole thing in context is, this is also a surface characterization technique. Okay, it depends on what is your surface, the way you are defining. Is a few monolayers from the top or 1 micrometer. If you this has the capability to give you the topmost 1 or 2 micrometer information. Quite often that is also important. It's not only the topmost layer, but what is there, this thing. That is how these techniques give you information, both structural and compositional information. That is how I'm just putting across that. Okay, and it has various resolutions depending on the interaction volume. Interaction volume becomes a very important parameter in deciding the whole capability of the technique itself. Okay, now then TM. Okay, TM also has a variety of possibilities and analysis capability. Except this, we are lacking this. Okay. And all other things are there available. You can exploit TM fully. Again, TM is a sort of analysis where you get information from 1 micrometer or less from your sample. But of course, TM requires a rigorous sample preparation, where from you reduce your bulk to that thickness before you make all your analysis. Okay, this is this thing. Now just to compare your optical microscope, SEM, TM, and AFM, the sort of resolution capabilities are compared here. Okay, and this has been pushed far beyond the state of what stands at 0.7 angstroms. That is what it is. It's sub-angstroms. That is what we have a machine. Okay, recently got installed. It's yet to go up for usage. Okay, that is having less than 1 angstroms resolution. That is a Titan. It's a aberration. It's a high resolution transmission electron microscope. Shortly, within a couple of weeks or so, it should go up for users. So that way, this has been pushed further. And again, this with the field emission gun, this can go to 2 nanometers. Optical microscope is the best possible. That is where it is like. Okay, AFM, of course, you can just go to 1 angstrom or so, and various other possibilities is listed there to just compare the techniques like. Now, just to briefly tell you about EPMA, the way EPMA analysis is done. Okay, you have your image, and imaging you can do, chemical analysis you can do in an EPMA. And this is the spectra. There are some unique differences how you obtain spectra from each one of these techniques, what is the information it can give, all that. Okay, the technique capability is put here. For EPMA, you have a spatial resolution of 1 micrometer. Relatively high analytical sensitivity. Okay, for most of the elements, this is the sort of sensitivity what you have. The detection limit, it's 100 ppm. Okay, for most of the trace elements. Okay, so that is this thing. This will be compared later. You will see how XPS and AES gets compared with that. Later we'll do that. Okay, and the whole setup looks something like that. I'm not spending a lot of time. Most of you have seen or gone through things. Just I'm putting like a recap and leading towards our today's discussion, that is XPS AES. Okay, so this is a EDS detector, this is a WDS detector, EPMA basic structure. It is similar to ASEM. The basic process is that this one, you have an atom, it has a shell structure, where incoming electron is there, it just dislodges or knocks off one of the inner core electrons. Once a vacant site is created, any of these transitions are possible, and that leads to a X-ray emission. And you can grab this X-ray emission, okay, and just from there you can obtain the material that comes as a spectra. For a certain amount of time, you collect the signal which is coming out. That is plotted as this thing. Because these shell levels are characteristic, then you can just decode what are the material, what are the elements present. That's how you just use a EPMA or EDS in a SEM. So there are 2 ways of doing it. One is the energy dispersive X-ray spectroscopy, what is generally abbreviated as EDS. The other is WDS, where you just are looking at wave dispersive characteristics, and then you just have your spectroscopic technique. Okay, there are some advantages, disadvantages, all these are there. Okay, a comparison is placed here, very brief comparison of EDS versus WDS. Okay, EDS, energy resolution, this is what it is. You see that it is relatively poor when compared to what the WDS can do. But you see here, there is an advantage. The whole analysis can be done in 1 minute. Here it is more than half an hour or so. Using very easy here, it is very little bit difficult. Okay, and standardless. Okay, it is not so easy or not done here. but more often it is handleless. You take your sample, just put it, you wanted to know the composition, just set it up for the scan, you just get that analysis. And the whole software and the whole the thing is so developed. The numbers what you get, if you have done the experiments correctly, you can just put your it has its own reliability, its own utility. Okay, peak to noise ratio, this is what it is. Okay, and WDS is 10 times better in that score. Okay, this is a typical spectra for a WDS and EDS. A comparison here for a particular scan is shown here. Okay, EDS, because of the poor energy resolution, each peak is very, very broad. And if you have any narrow details like that, you lose them out. And WDS can just, because it has a better resolution, it can reveal these peaks. And so that's the comparative this thing. Okay, and this is overlay to show this is the WDS part, this is the EDS part. Okay, this curve is for the EDS, and for the same energies, if you just see what is the WDS data, this is what it is. So this peak gets lost into this. Okay, in this when you are doing EDS, but all the same, it has its own advantages, disadvantages. EDS and WDS compared here, its characteristics. Okay, and so we'll not go into the details. Okay, now you can do EDS analysis in TM also. You have certain advantages, certain disadvantages. I just wanted to illustrate using this how you can just refine the what is the set of lateral resolutions that has been achieved by people, or what is the state of the art. The basic principle in TM analysis, EDS, okay, you have X-rays generated, that is captured by the detector. Okay, here is the detector, this is the TM column. Okay, this is electronitrogen cooling the detector goes in, and you get the signal acquired, and whatever is the whole thing is processed, and you get the whole spectra. And the process is, when your X-rays are coming, each individual photon is just grabbed, analyzed, and its energy value, because this EDS, we are looking at the energy, and this is the typical, this is the holder which goes into the microscope. This is where your sample is sitting. The sample area is 3 mm disc, 3 mm area, where you place your sample. If it is a powder sample, you support it with a grid and place it. Your sample is sitting here. That is where it goes into the microscope, and this is the detector part. That's how you just do the whole analysis. Okay, and the whole processing, how you do and all. This is the TM column. This is where your sample is sitting. This is the detector is sitting. It is picking up at this angle, whatever the details come, it picks up, and you analyze and get the information. Now, the advantage of doing it in TM, okay, you see this is a face, this is an image, there are so many faces, and you see the marker here that tells the size. If you take this and see, many of these are less than 50 nanometer particles. Now, with the TM, you can just take EDS analysis from selected regions. This is the whole spectra. So that way you can just take from 20 nanometer or even around that, or a little bigger particle, that area you can take a EDS analysis. The spectra, you are just narrowing down from your 1 micrometer lateral resolution, 1 micrometer volume, just coming finer. You are coming with the TM to this set of levels. How far you go? Our aspiration always have been whether you can get spectroscopy from an individual atom. Okay, whether you can see individual atom. We have achieved that. That's what I am wanting to place before you go to the next thing. This is at one level of analysis and mapping. Here you are doing the elemental mapping. This is an electronic device, STEM image, various components, various details. Now you want to see the distribution of image. There are different other things. Okay, elements of your interest. You can open as many frames as you require, as many numbers of elements you wanted to see. And each frame will show one individual element. This frame is showing only nitrogen. This is showing oxygen. Oxygen is all over here. Spurious color has been added. Okay, that is what it is. This is the silicon part. So in the whole device, how are these elements distributed? This is possible. Similar mapping possibilities are there with the XPS, AES, or in this thing. This is at one scale. We can do that. What is the advantage of SEM versus TEM? SEM, it is a, you see the accelerating voltage. This is the sort of accelerating voltage used in SEM. So you see the interaction volume. It's a very large. As against that, you see in a TEM, okay, the material is same. 100 kV, this is the broadening. 300 kV, this is the broadening. If your sample is kept thin, virtually there is no real broadening, and you can just reduce your lateral resolution to very, very small numbers. Okay? And we can just get spectra from very localized region. You can obtain spectra from various regions. This is a TM image. This is a whole marker to show the size, those things. You can just obtain at a grain boundary and those sort of whatever is the phase required. You can just get analysis. This is a scanning tunneling, scanning transmission electron microscope point analysis. This is the sort of mapping what one used to obtain about 20 years back, 15 years back. Okay, very poor quality. But latest, this is the sort of level of mapping that has been just achieved with the EDS in a TM. And these are the grains. This is the grain boundary. Okay, and these are the grain boundaries as provided by the latest models of EDS analysis systems. See the marker here. This is 30 nanometer. This is the length of 30 nanometer. Okay, and that is how you can just get this thing. You can get a line profile. From here to here, you can just get your composition variation. Okay, that is what is shown here. And as you are scanning across here, you are looking for variation in copper, atom percent. Okay, it just is this thing. At this boundary, there is an enrichment that just shoots up. At the grain boundary, the fraction of copper is more. Away from that, it is this much. At the boundary, it is this much. The segregation which is taking place there, you can just study. What is this boundary which is showing the segregation? This is the length of, this is the dimension or width of the boundary. How many nanometers? You can see here, this thing. Up to here it is 10 nanometer, 20 nanometer. This is a few nanometer, is the segregation. Okay, the analysis is possible. Okay, and these are available very much with our machines. Like now, this is another again grain boundary segregation, stem and dog. Okay, I'll just go to this thing. The advantage of having while doing it in a EPMA, SEM versus in a TM is shown here. Okay, and you see interaction volume is very large in EPMA or SEM. So when you are analyzing the number of atoms participating or giving your signal out is this many. And that is how it is a bulk analysis, although it qualifies as a surface because it is still 1 micron meter. Okay, if you take any material, still 1 micron meter is very, very small. But in the context of XPS AES, okay, this is at least 100 times or so more thicker. Okay, so that is where it is. Now in the TM, you make the sample very, very thin. That is the thickness. You can make it still thinner. and then your beam is interacting only here. The sample thickness is this much, you are thinned down to this much. That is where your high resolution images are done. Your high resolution imaging and analysis is done with this sort of thickness. Although this much of thickness is acceptable in a TM, but most of the analysis are even a little 10 times thicker also is okay with the imaging, but analysis is done in this sort of range. When you are doing this, your probe which is coming, how many atoms it is going to really hit and where from the information is going to come? It's going to come from single atom. Okay? Why single atom? There are very minimal number of atoms here. If you take what is the probability that some signal is coming and down, that works out to be, this is the ability of your EDS. With that, we can go down to about atom. What is that achieved so far? That is illustrated in this thing with the AEM. What has been achieved? Analysis capability is illustrated here. This bar is more illustrative. This is number of atoms. You see here 1, 2 atoms, 5 atoms. That is where it is. The instrument detectability limit is shown here. The instrument, 2 different instruments are shown. This is a usual TM. This is an aberration corrected TM. Okay, we are almost having a machine with this capability. Not really, because we have not yet to add this, but almost with this sort of capability. A little bit poorer than this, but that is where it is. Our Titan machine, which will go up in a couple of weeks, will have this sort of capability. So where is the analysis limit? Almost 1 or 2 atoms. These are the experimental values shown. We are there about 2-3 atoms cluster. We will be able to analyze. What is the mapping capability? This is the mapping capability. Okay. And again, this is more illustrative. This is the number of atoms. This color matches with the 0 atom. As you go up to here, it is 10 atoms. 10 atom is the brightest. The color gradation here indicates how many atoms lie. Somewhere here it will be 5 atoms. That color, whatever you are seeing, 5 atoms. This is a mapping. Again, taking the mapping to atomic scale. That has been achieved, demonstrated. People are using it. Okay. And that is where the technology has gone. Okay, and if you compare EPMA versus EDS in a TM, okay, then it is if you take minimum detection limit, it is almost a few million better than EPMA. Okay, because EPMA is handling millions of atoms. 3 million atoms it happened when we were probing. About 3 million atoms are participating. As against that, in a TM context, when you are analyzing, only 1 atom is participating. That ratio, if you take, is 1 million times better. That is the sort of possibilities. Our machine, the new TM which will be there, okay, will have almost this capability. Okay, almost this capability. Marginally less, but almost this capability. We are having one of the best EDS with that. Now, another thing I want to illustrate is the yields possibility in AEM. Okay, this is another electron microscopy technique, the electron-based spectroscopy technique, which can be put onto a TM. This facility is not there still, but this can be very much added to our new machine. Once that is added, that will be the most powerful characterization tool, okay, to give you the best possible information. Okay, and this is a typical spectra and all. Okay, and this goes as again with the XPS, AES, this and SIMS. These are the 4 real surface characterization tools to get you the information. Okay, the typical machine and all I have shown. Okay, and this the details of the design and all. What is just relevant is this, the sort of energy resolution what you can get. This is the fraction. Okay, the sort of energy resolutions what you can get. Okay, with various guns. This is the sort of this thing. Okay, monochromatized. If you have a monochromatic field gun, okay, this is the sort of resolutions achievable. Okay, I just skip this and go here. Okay, now with this sort of possibility, with these yields, what is possible is illustrated in this slide. This is an image. Okay, atomic resolution Z contrast image. That our new microscope can do this at this level. Our present microscope also can do it, may not be at this level because it's not a dedicated HR chem. But the new HR chem will be able to do that. Okay, this is the image. This each one of, to crudely put it, each one of these right radii is a column of atoms. If your sample is only 10 nanometer thick, maybe this in this direction about 20 atoms or 30 atoms are sitting, but all the same it is a column of atoms. That is where it is. Now your probe, Yields probe, is looking at spectra along this column, along this column, along this column. For each one of these column, okay, of atoms, these are the spectra shown. Spectra shown. You come to this, the spectra is showing some characteristic this thing. From there, what is this edge you can work out by the Yields analysis technique, and you can see that it is a lanthanum. This is a M42 edge. Okay, you are able to now do spectroscopy from individual atoms or individual row of atoms. So that is what it is. So you are just, your probe is seeing this column and getting the spectra like that. So that is the sort of capability that has been achieved. Now that put here, it is in the Adolf high angle dark field in a STEM mode. This is the image, and these dots, what you are seeing, bright dots, are your atoms. See this marker? That is 0.5 nanometer is 5 angstroms. So these are all in atomic resolutions, atomic scale what you are talking. Okay, this is the grayscale image for the same, using the X-rays. Here you have gallium and arsenide. Are you able to distinguish that? Yes, the present machines can do. You are just having here the ability to see your images or structural information at atomic level. And also, not only that, you are able to now, from your X-ray, K alpha, you are able to identify what is that atom, and that is shown here. This is spurious colors added. With that, you can see that this is the color chosen for arsenic, this is the color shown for this. The overlap of that is shown here. Okay, both are shown here. You use Yields. So this edge, now you are able to locate or do a mapping. This is a mapping, not at microstructure level, atomic level. These are possibilities. This is the state of art which is there existing like. This is our old machine, our present machine which is operational, our MSc machine. These are the machines which used to view as atomic resolution. And these are the set of machines which used to be developed to get this set of resolution. Huge structures, okay, hundreds of feet. This is where the operator will sit. Okay, that is the number, but with all innovation, that is the machine what we are having, Titan. Not with this number, but close to 1 angstroms. Our machine, I heard that it has been, on this machine, it has been demonstrated 0.8 angstroms. So our machine has been just handed over to us with 0.8 angstroms resolution. That is the machine what we are having. Okay. Now to just put the whole thing in perspective, TM, okay, imaging, these are the imaging possibilities. SEM can go up to about this sort of size. FSM pushes it farther, okay, about this sort of size. With them, we're just there going to 1 angstrom. That is the structural capability. These are of course bulk analysis. Other various analysis level, this thing. Your XPS, AES, the XPS, SCA stands somewhere here. Okay, micro extra can push this scale a little bit this way. Okay, and what is the analysis capability? This is the band. Okay, composition. Okay, your SIMS can give PPB level, and time of flight SIMS can give this level. And your AES, XPS can give information in this level. What is our machine going to give? You will be just told in a short while from now. Okay, the whole basis is this. You have a probing signal coming and falling on the sample. You have a data coming out. Once you have the data, there are infinite possibilities. Okay, it's not just this thing. There are infinite possibilities. Again, that will be illustrated how XPS and AES it is. So this thing with illustrative examples, it will be shown to you. But of course, in a particular scenario, it narrowed down. How do you narrow down and come to understand that meaningfully? That's the whole exercise of characterization. You have many spectroscopic techniques, XPS, AES, yields. These are the electron-based techniques. For surface analysis, these are the ion-based techniques, or SIMS, and these are there. Okay, and the whole basis of this analysis for surface is a surface sensitivity. When your incident radiation is coming, it just goes in, gets scattered. If you can see just only one scattering event after that, whatever it comes, then it carries the information of this material very effectively. That is what you use in any spectra or this spectroscopic techniques. Again, that will be illustrated to you further in the future talks and all. The whole thing comes from this elastic mean-free path for elastic scattering, okay, inelastic scattering. If you take for typical material, okay, magnesium as a radiation, if you take carbon, oxygen, and nitrogen, typical mean paths for this. These are the main paths. And what peak you see usually comes from this depth, at best twice this depth. That is what it is. For carbon, okay, at best about 2 times or 3 times this depth is what is contributing to the carbon peak. And similarly, there will be sensitivity variations for various distinct. And if you take XPS, okay, your X-ray beam which is going to come and incident is going to penetrate quite a bit. This is your sample. It is going to irradiate a large area. But your analysis given by this is surface sensitive, okay, or surface analysis. How is that? Because of the whole process how it takes place, okay, this information is really not seen in your spectra, or it is there existing only as a background. And what you see as a peak is from this red area, hot area. That area, if you take, that is that. Okay, this depth is what is going to contribute to you in your whole image analysis. So in XPS, AES, when you obtain, that is where from you are going to obtain the information. Okay, these are relative sensitivities. I'll skip this. I'll again put this just comparison. This is your scanning OJ, and this is your typical EDS in a SEM. If you see the area, 1 micron-meter depth, 1 micron-meter width, this is the interaction volume. So that's what it is for X-rays in a EDS or a EPM, in a SEM when you are doing. TM, because this bulk is not there, once you make it thin, you can just narrow down on that, going down to that capability what just I mentioned. Now about XPS. XPS, the whole this area is irradiated. The whole this thing is just giving signals, and this yellow, what is shown, is what is contributing to your spectra. What is that depth? That depth is shown here in nanometer. Okay, and this is the depth for AES. Again, AES is coming from here. Okay, what is that depth? This is the depth. That is what is used in scanning OJ microscopy. So that is where these two techniques, this and this, becomes a surface analysis technique, and this to differentiate the bulk of this thing. Just to introduce, the whole XPS is based on this photoelectric effect, okay, and this is the statement on which it is based on, and the quantized nature of light is what is used, and just this thing, the basis is this. You have your primary, that is X-ray, interaction is photoelectric effect, and the secondary, this thing, signal what you just measure is this electrons. So you have your in-gate coming X-ray photon, just interacts, and it releases one of these electron out. This carries the energy, okay, part of it is used to release itself, that is equivalent to the binding energy, and part of it is carried as kinetic energy. That is what you measure. This is the whole process. The idea is this. Okay, you have incident photon, knocks off, and it carries this thing. That is the photoelectron, what you are going to grab. Okay, this is our machine. Okay, this you are going to be talked about today. This I keep claiming to whoever visited the lab, telling that this is the state-of-the-art machine. Yesterday I verified with our expert. Okay, I did ask that whether it is this thing. He told, yes, this is state of the art in its own right. To just demonstrate and explain to you how it is. Okay, and also I keep claiming our machine in this country is the best, having the most packed capabilities. That is also true. That again you will just explain and impress upon you. Although about half a dozen machines are there, ours is having an edge over other machines. Okay, this is the whole basis. You send an X-ray, it scans. Okay, electrons are generated. Okay, and just that analyzer takes it, analyzes that. That is a spectrometry of time. This is what it is. You have this monochromatic radiation put onto that. This is your surface with certain number of monolayers participating, individual atom illustrated to show. This is your electronic cell structure. And once this interacts, you just get to obtain a spectra. Each one of this is correlatable to these electron shell levels. That is how you decode the material, and how best we do, what are the pitfalls, what are the difficulties, it will be explained to you. Okay, I stop here. I thank you for your patient hearing. I will not have any discussion, we'll go to the next topic. Okay. I welcome Dr. Sundararaman, as I have circulated the mail and shown it. He has a vast experience, and he had been there in industry, academia, and also he has been just traveling to various places, educating people in using this thing, XPS the best way. Okay, so I just hand over the stage to him, and it's